Welcome back to the channel. Well, we've had some snow lately and outdoor play has been canceled. So today, we're going to stay inside the warm shop and I'm going to go ahead and build an adjustable electronic ignition system for a small engine. Now for our project, we're going to custom tailor this ignition system to fit the 212cc Predator engine. But the basic components used in this project can be applied to any small engine if you use your imagination. Now, the magneto ignition system on this engine is fine and there's absolutely no reason to change anything. Basically, this current ignition system will provide years of trouble-free service, but that's no fun. On this engine, well, the spark is generated when this magnet on the flywheel passes under the magneto. Of course, this is a modern engine and it doesn't have points, and the ignition system's solid state. Solid state is such an old word nowadays, but back in the 70s it was all the rage. Anyway, the ignition timing is somewhat adjustable, but you have to use these offset flywheel keys. Now, what offset is the best? Well, that really depends on the load and the RPM, but generally speaking, advancing the ignition system a little bit is always good. So you may ask, Jimbo, why do you need to adjust the ignition timing while the engine's running? That's a good question. Well, we have a few very cool experiments coming up in future episodes, and we definitely need variable ignition timing and a few other things. That's the big picture. And in future episodes, we'll exploit the ability to adjust the ignition timing while the engine's running, because who doesn't love to torture a small gasoline engine? You know, for science. Now today, I'm going to build something that's unnecessarily complex to suit my own purpose. However, like I mentioned before, the basics of this system can be applied to pretty much any small engine. That's enough talk. Let's go ahead and do something fun for a minute or two. Okay, the engine we're going to test today is a brand new 212cc Predator. Well, sort of brand new. You see, this engine was purchased about 5 years ago for exactly $99. Good luck finding one of these today at that price. Anyway, this Hemi version of the Predator was unboxed today, and it has less than a minute of actual runtime on it. And that was just to confirm it actually runs. The engine is connected to a 140-something amp Delco alternator from a Cadillac. We use this alternator to put a load on the engine. Now, it's a rudimentary system that we use for testing engines, and it's not precise, but it does the job. Now, the load bank has seen better days, and we're going to have to scrap it real soon. You see, we've used this test stand to experiment with the little diesel engine, and the vibrations from that engine have pretty much destroyed all the load resistors. Hopefully, some of them still work. The plan is to eventually convert this test stand over to liquid-cooled resistors, which probably sounds exotic, but it really isn't. It turns out it's far cheaper to use hot water heater elements in a barrel full of water than it is to replace these very expensive resistors. But that's a project for another day. Over here, we fitted the engine with a standard degree wheel, which has been calibrated to show true top dead center. This little dot is the magnet for the tachometer. Now, I always get questions about the simple low-cost tachometer that we use, so I put a link in the video description for the $18 tachometer, and I talk about it in Season 2, Episode 28, and in Season 4, Episode 3. It's a cool 12-volt digital tach that'll measure shaft speed on pretty much anything. Anyway, right now we're set up to gather some baseline data on the little engine, so let's do it. Okay, let's find out what the stock ignition timing is for this engine. Now, due to the camera shutter speed not being synchronized with the timing line, well, it's sort of difficult to capture the timing on video, so we'll do a snapshot. And there you go, the spark plug is firing at about 24 degrees before top dead center on this engine, which seems reasonable. Of course, that's at 3,700 RPM. Now, since this engine has fixed ignition timing, we should pretty much see the same at idle. So, out of the box, this engine idles at 1800 RPM, which seems like a lot, but the idle can be adjusted to go a lot lower. 1800 is fine for today. And once again, it's difficult to get this on camera, so let's do another snapshot. It looks like we got a slight drift in the timing, and at idle we're about a half a degree more advanced. It's pretty much the same though. Well, I reckon it's safe to say that the magneto ignition fires the spark plug at about 24 degrees before top dead center. It'll be interesting to see what happens when we change the timing in either direction. And now for the tough part. We're going to have to fit all the gizmos for the ignition system on this side in this very limited space. Alright, let's talk about the stuff. For the ignition coil, we're going to be using a coil pack from a GM LS type engine. These coil packs are located on the valve covers of these V8 engines, and it's one coil per plug, or COP. No, not that kind of COP. COP means coil unplug. Now, the reason we're using this type of coil is they have a built-in trigger amplifier, and what that means is you don't need a separate high-power gizmo to get these coils to spark. Nope, all it takes is a 5-volt signal and about 50 milliamps to trigger the coil. So when we look at the pin side of the coil, it's labeled A, B, C, and D. Pin D is the battery voltage, which ranges between 11 and 15 volts, but is generally referred to as 12 volts. This pin carries a lot of current, and the wiring should be able to handle at least 10 amps. Figure a 16 gauge wire should do it. Pin C is the 5 volt trigger signal. Now this coil will spark the moment it sees 5 volts on this pin. These coils have a 3.5 millisecond dwell time, and I'm not sure how important that is as far as overheating the coil. You see, on the bench, I greatly exceeded the dwell time with no issues whatsoever, and there appears to be some sort of gizmo inside the coil that prevents oversaturation on the primary side. No idea what's going on, so we shall remain ignorant of this feature, whatever it is. The bottom line is, the dwell time is not an issue with this system. Pin B is the return or ground for the trigger signal, and Pin A is the coil ground. Now, a lot of folks like to tie these two grounds together, but keep in mind, internally these grounds do not go to the same place, and there's about 100 ohms of resistance between these two grounds. Tie them together if you want to, but for proper electrical hygiene, these two grounds should be separated. Pin A goes to the engine block, and Pin B goes to the device that provides the trigger signal. Okay, so here's all the junk needed to get the ignition system to work. We just talked about the LS type coil, which you can get from a junkyard or buy it new from the Jungle site. The pigtails are also available for these coils on the Jungle site, and that makes wiring a lot easier. Now this guy is an inductive proximity sensor. This you cannot get on the Jungle site. Well, in fact, Amazon does sell inductive proximity sensors that look exactly the same as this, but they do not work the same. And what I mean by that is, the sensors on Amazon are not rated for frequency, and they're way too slow to be used as a crank position sensor. I ended up getting this sensor from Automation Direct for I think about $25, and that's money well spent. This sensor is rated for 1000 Hertz, so that means it can switch on and off 1000 times per second. Now we really don't need something that fast, and given that the valves on a Predator engine will float at close to 500 RPM, we only need something that can handle about 80 Hertz or 80 times per second. The Amazon proximity sensors probably switch at 2 or 3 times per second, and they're completely unsuitable for something like this. Now I went with an 8mm sensor because I wanted the components to be as small as possible. You can get other type of sensors like Hall Effect, but they're a lot bigger, and I think for something like that, 10 or 12mm is the smallest you can go. Anyway, this inductive proximity sensor will detect a rotating steel thingy that we can easily build, and that makes everything a lot easier. For the folks who know what's going on, you can build this trigger system however you want, with whatever sensor you want. But to make it as small as possible, you're kind of limited to using an inductive proximity sensor. Anyway, to mount the sensor, I used the 5/16 coupler nut that's available at any hardware store, and I drilled it out with a 7mm drill bit, which by the way, still leaves some of the SAE threads behind. No worries. Then I chased the threads with an 8mm by 1.0 tap. Now, despite the somewhat hodgepodge build, at the end of the day, this guy will hold the sensor in place no problem. Oh, and then I welded the coupler nut to a piece of 16 gauge steel. Now, I could have just 3D printed something from ASA filament, but I did this old school because I can roll both ways. Now let's look at the black box. This guy holds the 5-volt regulator and the MOSFET transistor. To some folks, this may look scary because it's hand-built electronics, but I couldn't find an off-the-shelf solution for a high-side switching transistor. You can get low-side switching transistor modules no problem, but you can't find high-side switchers for some reason. Anyway, the schematic for this transistor looks like this. Now underneath the transistor board is a hand-built 5-volt regulator, and it's made from a 7805. You could buy an off-the-shelf 5-volt regulator for a few bucks, and I just made my own. The complete circuit for the ignition system looks like this. This guy is the inductive proximity sensor, and when it senses the steel thingy approaching it, it'll switch from 0 volts to 12 volts on the output. That 12 volt signal gets fed to the gate of the MOSFET, and that'll trigger the FET to turn on and allow 5 volts to flow from the drain to the source. Now, this 5 volt signal will go from here directly to the trigger pin on the GM-LS type coil pack, and that'll command the coil to instantly spark. All this stuff happens very quickly. The resistors I chose, well, they work fine, and the values are not set in stone, and anything close will work. I'm not sure, but it may be possible to drive the coil pack directly from the sensor, but it may get a bit sketchy, so I took the path that I know will work. Anyway, nothing on this circuit is overtaxed, therefore no heat sinks are required. Let's put this back in a box so I don't scare any more people. Now, in the video description, I'll put links to all the stuff I used, and you can pick and choose what you like and what you don't like if you decide to build something like this. Let's go ahead and take a look at the mechanical side of this build. So off camera, I built all this stuff. The good news is this is all fabricated with common hand tools. I did cheat a little bit and used the lathe to clean up the edges on the backing plate, but the lathe really wasn't necessary. Anyway, here are all the components. This is the backing plate that had its outer edge cleaned up on the lathe. Now, this is a $16 Lazy Susan. You gotta wonder how this type of bearing got that name. Was Susan really that lazy? I guess we'll never know. Anyway, Susan's got a job to do now, and she's what makes the ignition system adjustable. Good job, Susan. The crank position sensor attaches to Susan like this, and that way we can vary the location of the crank sensor. It's a real simple system. Now this thingy is what will trigger the crank sensor, and it clamps to the crankshaft on the engine. And when the crank spins, this guy will pass in front of the sensor and trigger the coil to spark. So this thing's made from a 3/4 inch 2-piece aluminum shaft collar. These guys cost about $5 each. Now what I did was, I drilled and tapped a collar for a 5/16 by 18 thread, and then I used a cut down 5/16 bolt. I reckon the metric people could probably use an 8mm bolt or whatever floats their boat. Now at first glance, it may look like the bolt is a bit too long, and yeah, I would agree, but this is a work in progress. Now if I cut down the bolt to about here, well, that seems a lot more reasonable. However, then I may run into a possible problem, and I may get a false trigger when one of the clamping bolt passes the crank sensor. This is one of those problems that take a lot of time to work out because it involves a lot of fiddling. Now, you may have a bunch of time, but on my side of the fence, I have a very limited amount of time to make all this stuff work while also producing a semi-quality video. I will of course sort this out off camera, but for today we have a workable solution. Now you really can't set up the ignition timing willy-nilly, and it's very helpful to have a degree wheel plus a top dead center finder. These two gizmos got used pretty much in every step. There are tons of videos on how to use these tools, and I'm not going to get into that today. Just know that this stuff is required if you want to know the actual timing settings. So we're going to be using this side of the engine for our ignition system, and that's because we have the room for it, and I want to avoid fooling around with the flywheel. Now this chunk of cast iron has a lot going on that you might not be aware of, and modifying a flywheel is the same as pulling the pin on a grenade. You see, the centripetal forces acting on the flywheel are immense. Now if you've never attended a Physics 101 class, then you wouldn't know this. Anyway, there's a lot of scary math involved, and it's best not to experiment with flywheels if you don't know the math. And that's because it doesn't take much to get one of these flywheels to explode, so we're not going to be messing with the flywheel today. Now I'm building an ignition system that's adjustable while the engine's running. However, basically with the same components, you can still build an adjustable ignition system, except you'll have to shut the engine off to adjust it. Something like this would work, and you can use the degree wheel to set the timing to whatever you want, but we ain't doing that. So this is the backing plate that goes on first, and it gives Lazy Susan a place to sit and be lazy. Anyway, I have to put a thin washer between the backing plate and Lazy Susan to provide a slight amount of clearance to avoid the parts rubbing together. Next goes on the crank sensor and the adjustment arm. The adjustment arm is actually made from thin fiberglass, and it's basically the same stuff printed circuit boards are made from. It's easy to cut and it's lightweight. And now I can install the rotor. Now this rotor has to be dialed in with the degree wheel. Unfortunately, the degree wheel gets in the way of the camera, so let's pretend we have the crankshaft set to 24 degrees before top dead center. Basically, the rotor needs to be rotated right to the point where the light turns on the sensor, and that'll cause the ignition to spark exactly at 24 degrees before top dead center. Anyway, at this point, the rotor can be clamped to the crankshaft. Now, given that this doohickey is a lot longer than it really needs to be, we're going to have a slight imbalance. But keep in mind, since we're close to the center line of the crankshaft, the amount of imbalance will be nominal. And no worries, eventually we'll fix that. Today, we're more interested in verifying that this system works, and we'll fine-tune the details later. That's how it works on YouTube. Never enough time. Oh well. Okay, we have the ignition system installed and the basic timing is dialed in. But before we start the engine, let's confirm we have spark. Yep, I can hear it spark. It's sort of hard to capture on camera though. Yep, we have spark. I have the timing set so the spark happens at about 24 degrees before top dead center, which is the same as the magneto ignition. Just for fun, let's start the engine on the magneto ignition so we can confirm we have spark when the engine's spinning faster. Now remember, the engine's running off the original magneto ignition and not the new ignition system. Yep, it looks like the custom ignition system's working and we get spark at higher crankshaft speeds. That's awesome. Okay, let's go ahead and shut off the magneto ignition and connect the custom ignition and see if the engine will actually run. Well, the LS coil pack is connected to the spark plug, so let's see what happens. Now, the timing is set to about 24 degrees before top dead center, or something like that. Basically, it's close enough to the original ignition settings. Let's see if the engine will even start on the custom ignition system. Wow, it started right up. Very nice. After a few minutes of runtime, the coil pack is still ice cold, so that's good, I guess. Let's fool around with the ignition timing. Wow, that moves quite a bit. So it looks like we can go up to 47 degrees before top dead center, which seems extreme, and you can hear the engine's not 100% happy with that much advance dialed in. Interesting. Okay, well, this thing is stinking up the shop, so let's shut it down. The coil pack is still ice cold. Very nice. Fast forward a bit and we have the alternator connected so we can put a load on the engine. And over here we have our display. This is the RPM, this is the voltage at the battery, and this is the current or amps that the alternator is producing. Now this is the control box for the load center, and unfortunately most of the loads no longer work, but I think one or two may still work. Now when you factor in the less than ideal efficiency of the alternator, which is about 60%, the engine should be able to handle about a 3,000 watt load. Of course, when you do the math, the 6.5 horsepower engine should be able to carry a much bigger load. But keep in mind, when it comes to alternators and these little engines, well, I have plenty of experience fooling with this stuff last year when we were experimenting with the petroleum battery golf carts. Anyway, we learned that 40% of the engine's power is wasted when you convert horsepower into watts. That's just the way it is. So the folks that want to argue the math, well, keep in mind the alternator is only 60% efficient on a good day. Of course, the numbers I'm spewing are just approximate. Anyway, it really doesn't matter today because our load center is pretty much foobar and we'll likely only able to do a light load on the engine. But it should be enough for a quick experiment. Alright, let's light this candle. Contact. Clear prop. Okay, keep an eye on this number. This is the amps the alternator is putting out. This switch turns the alternator on. And it looks like we're charging the battery. This switch turns on the cooling fans for the load bank. Now let's find out which loads still work. Nope. Nope. Yep. And nope. Well, that sucks. We only have one load that works. Anyway, we have 34 amps showing on the gauge, which works out to be about a 500 watt load. And that's about 15 to 16% of the capacity of this engine, so it's a very light load. Let's go ahead and find out what the best ignition setting is for this load. Now when I move this lever down, it's advancing the ignition timing. If you watch the RPM, you can see it go up as I advance the timing. So it would appear when the engine's under a light load, it likes a bit more ignition advance. Now keep in mind, it's only a light load on the engine and this seems to be what works fine for this load. So the stock ignition timing for this engine was 24 degrees before top dead center, and the optimized timing is 33 degrees before top dead center. That's quite a bit of a difference. Anyway, that's just a quick experiment just for fun. We need to dig deeper into the subject because that's not enough information, but it does show that there's potential for improvement. Now, of course, too much advance under a heavy load is not a good thing. And of course, in an upcoming episode, we'll torture this engine and find out how much advance is too much. You know, the stock 24 degree advance may in fact be the best compromise under all load conditions. The LS coil pack is still ice cold, so whatever dwell time we have seems to be okay for now. Well, today we had some fun and I was able to work out the basics for a custom ignition system. Now, I went above and beyond to make this system adjustable on the fly, and that's for future experiments that we have planned. The basic system doesn't need to be as complicated, and all the adjustable garbage isn't really necessary on most stationary engines. Hopefully some of you folks can use your imagination and apply some of the things that I showed you today on a project you may be working on. I think the LS ignition coil plus the inductive proximity sensor paired with a buffer is all you really need to build an electronic ignition system for pretty much any small engine. Those are the basics, and the rest is a bit of fabrication and a few nuts and bolts. Maybe a little harder than that, but you get the idea. Anyway, we'll see you next time. Until then. Hey, thanks for watching to the end and watching this update. Well, this circuit is safe, it's reliable, it's robust, and it works great. It's old school engineering. However, for some folks, it may be way too complicated and possibly unnecessary. Just for fun, I went ahead and tried this circuit, and it turns out this simplified circuit works and the engine runs perfectly. In this circuit, we pretty much drive the LS-type coil directly with the sensor. Now, due to the incompatible voltages, I used these two resistors to make up a voltage divider to drop the 12 volts down to 6, which is close to the 5 volts the LS coil pack is expecting, but not close enough. Now, I could fiddle with the resistor values and get a perfect 5 volts from the divider, but the source voltage from the battery can vary between 12 and 15 volts, and no resistor voltage divider would be perfect. So I went ahead and used a 5.1 volt Zener diode to clip the signal voltage to exactly 5. This is a much simpler circuit, and it uses a lot less parts, and it works. It's a valid design, but it's not forgiving. And what I mean by that is there's no margin for any variances in the sensor or the ignition coil. This circuit works fine for me, however it may not work for everybody. It all depends on the sensor and the coil pack that you use. Now this circuit uses a field effect transistor, or FET, to buffer the signal from the sensor. This guy acts like the middleman and takes the signal from the sensor and passes it on to the coil in an orderly fashion. Plus, it's using clean and regulated voltage from the 7805 to produce the 5 volt signal the coil is expecting. It's one big happy family, and it gets the job done even if the coil pack or the sensor are out of spec. I know this circuit would pretty much work forever. You know, I've been involved in the electronics industry one way or the other for the past 30-something years, and simplification plus cost cutting is always a priority when dealing with consumer electronics. Now, if you haven't noticed, well, pretty much everything these days is crap, and it doesn't last very long. Yep, some of that can be blamed on oversimplification for cost-cutting purposes. Anyway, I reckon I'm going to go ahead and use this simplified circuit for now because it may be fine, and it'll be interesting to see if it'll hold up for long-term use. I mean, it really should, but you never know. Thanks for sticking around, and we'll see you next time.